Keying is one of the most fundamental tools for image, broadcast, and film production. Today, chroma keying is the most common matting method. The dependence on foreground color and problems of color spill are its two main disadvantages. We show how temporal backgrounds that alternately change their color rapidly at recording rate can aid chroma keying by transforming color spill into a neutral background illumination. Sequentially, recorded video frames are separated into image pairs depending on the backdrop color. Chroma keying is applied independently to both frame sequences. The resulting alpha mattes contain partially misclassified pixels when foreground and background colors match. The maximum of both alpha mattes is free of miscalculations. The mattes of two subsequent recordings are combined, the recordings are averaged, and the result is keyed. The outcome is completely keyed foreground with neutralized color spill. Our approach benefits from all advantages of chroma keying while overcoming its limitations, such as foreground dependency and color spill. Compared to digital color spill suppression, our method is automatic, supports real-time rates, and reproduces color correctly. Compared to conventional chroma keying, it is invariant to foreground colors, enables ad hoc adjustments of scene lighting during recording, and makes a uniform background illumination easier to achieve. If, however, the content in two consecutive images becomes misregistered during fast movements of the camera or the foreground, this leads to miscolored seam regions in the blended image and consequently to artifacts in the composite. An additional post-processing step identifies these regions and color corrects the artifacts by reconstructing the missing foreground information. We binarize the maximum alpha matte first. Then we find its contours by applying a canny filter. Next, we extrude these by dilation. The intersection between the binary matte and the extruded contours gives us the region with potential color seams. They are determined by comparing the absolute RGB color difference between both input images and the background colors. These pixels are handled in a color seam correction step. If the pixel contains the background in both frames T and T+1, they can simply be averaged without any further processing. The same applies for the case when the pixel image contains foreground information in both frames. If one frame was captured at time t and contains background, and the next frame at t+1 and contains foreground, then we compare the foreground pixel at t+1 with the corresponding pixel in the frame that was recorded at t+2. If this is classified as foreground, then both pixels are averaged to compensate their color spill. In the rare case of quickly moving thin foreground objects, a look back or a look ahead in the frame sequence will point to a background instead of a foreground pixel. If this applies, we carry out a spirally increasing spatial search around the original foreground pixel to identify the closest neighbor which has foreground information in both input images. We don't simply average them as before to compensate spill, but assume that the foreground color of the original and selected neighbor may vary slightly, but their color spill is the same. We extract the color spill of the neighbor and use it to neutralize the color spill in the pixel, which is currently analyzed. Color seams that are caused by movements of the foreground are removed in real time. Note the correct composition of the semi-transparent blanket with the synthetic background. This is another example. Again, the visible color seams are effectively neutralized. The synthetic background behind the flowers is a plain black image. Using the maximum of both mattes makes our approach insensitive to unregistered image pairs. The triangulation method presented by Smith and Blinn fails in this situation, since it only supports static scenes and cameras. This is shown in this example. For synchronizing the temporal backdrops with the shutter of the camera, we utilize the camera's composite output signal as an external trigger. We implemented different prototypes of temporal backdrops: a softbox with integrated RGB LEDs, a RGB front illumination of a diffuse background surface, and a back projection screen. The foregrounds are lit with arbitrarily aligned spotlights. Temporal backdrops that are realized with display technology can be coded temporally and spatially. The additional spatial coding can support camera tracking. The composite displays the result of a perspectively augmented image on the background plane. We compared our color spill neutralization approach with common software spill suppression techniques. A scene with a uniformly lit white background serves as ground truth. The The remaining color spill is calculated from delta EAB chrominance distance and CIE label color space. While on average, such techniques reduce the visible color spill only by a factor of 1.4 in our experiments, our technique compensated by approximately a factor of 4.4 down to a value of 2.6. Note that a delta E value of 2.3 represents a visibility threshold and equals 1 just noticeable difference. Besides visual effects production, we envision applications for temporal backdrops in other domains, such as novel game interfaces.